Farhan, go right ahead. If you would please introduce yourself and tell us a little bit about yourself.
Sure. Thank you, Anthony. This is Victor United 2, Echo Sugar Echo. Tit, 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 tit. And I'm a home brewer, been home brewing for a long time. And when Steve graciously offered me a slot to speak this afternoon, I was just overwhelmed with this whole idea of speaking to the very people who are, such legends. It's like equivalent of probably, performing with Clapton or Mark Knopfler or something like that. But I realized that, more than speaking, I have to up my game and bring some new learning to us all, me most importantly. And so what I'm going to do is not simply, describe a circuit or a technique or whatever, but, take everybody through the journey of making it through that. So that's my plan. And a little of background is in order, and I'll just take a minute to, finish this off first so that we can, from here go forward. So when I started out as a teenager, right, with the exception of Sprat, and Sprat were very difficult to come by in India, I would be looking at these articles from Pat Hawker's books and stuff like that. There's a British Council library here, which is full of the RSGP books. Um, and many a times I've tried building a whole direct conversion radio or something, and nothing would work. And I tried this for a long time and never really managed to get a whole radio going. Sure, I could make a crystal oscillator or an FET VFO going, and or a power supply with a 7805 regulator or something, but I could never get anything with more than 3 transistors to work. And it was a great puzzle to for a long time for me, that how do people like George, Doug or Wes manage to build these radios with tens of transistors in such complicated ways, and it all works so magically. I mean, it was frustrating and horribly unfair, I would say. So, I would solder all this together and keep staring at it for hours, saying, hoping I'd wake up from this nerdy nightmare and, get on air with the blasted QRP transmitter. Sadly, no cigar. So, um, I I figured that, either these people were, possessed magic of some sorts, or they were frauds who tricked young kids to spend their meager pocket money on electronic components instead of buying more dangerous stuff that the money could afford them. Um, well, all that changed pretty late, I should say, for me. In 2002, I started reading the Experimental Methods and Art of Design, and it solved this great mystery of why I couldn't make anything with more than 3 transistors work. So it was simply this, that all radios were ultimately built with 3 transistors at a time. So it was like a revelation. I was building 2 transistor circuits that blinked lights, generated frequencies, etc., etc., audio amplifiers and LM386 or something, but I just had to build them one module at a time, test and move on to the next small one. And I also realized that there were just 4 circuits that you ought to know how to build, right? There were filters, a band pass filter and a low pass filter. It's pretty easy to do if there's just coils and capacitors. Uh, how to build an oscillator. Mixers, you could just get by with diode mixers, which is just 4 diodes and 2 transformers. Um, and of course, amplifier, one amplifier could actually last you a long time until you came to the power stages. So once I figured this out, then I started building stuff, and following this idea of building small blocks, measuring them, and integrating them into a big radio, I thought I'd do that almost live. Meaning that last 1 week from 1st September, actually 29th onwards, I started building a new radio, and this new radio was something I wanted to do, which I had never done before. As a result, I have now developed a BitX, which is meant for 2 meters, 144 megahertz. So it covers 144 to 146. It's almost done. Now, the thing was that I just had a week to work on this. So right now it's got only 100 milliwatts of output, and I'll, when we go through this, we'll figure out why it's 100 milliwatts of output. But let me, start the presentation itself, so we'll be able to, get on with that. How does one start presentation? Let me just put on my. Do you have to give me some permission to? Share screen. All right. Host has disabled participant screen sharing. Anthony, could you allow me to?
Yes,
Farhan, it's been done. Should be okay.
Yes.
Okay. Yeah, share screen. All right, we've got that. Desktop. Okay, here we are. So, okay. So can everyone see the screen now?
Yes, we can.
All right. So this is what my presentation is about, and there are a lot of slides, and I'm going to, walk through them, stroll through these. So just note down stuff that you might want to ask, and I'll get back to it. Okay. So let me start here. That we should be able to good to go. Okay. So let's build a VHF SSB QRP radio. Now, I chose this because not many of us have tackled VHF projects. I mean, all the time we end up building HF rigs. So why not look at what's above 50 megahertz? The only difference really was to keep the wires short. But apart from that, there's not much else. But for the fact that, we did not have, or rather, I did not have the instruments to really measure too well, and I'll figure out and I'll explain to you what I could measure and what I couldn't measure, which I had to guess and get through with all this stuff. So essentially, it might even get a little boring. That's we design a particular module, build it, measure it, repeat. So that's how it will go. Now, for those people who don't want to go through it all you have to do is go to this my GitHub, which is github.com/afarhan/bitex2m, and start building it while I talk to others. Okay, so let me start first by looking at the simplest possible SSB transceiver. Okay, so this is what can be the simplest radio, right? There's a ladder filter with 2 mixers on both sides. And on one side, you have a band pass filter. On the other side, you have a mic and an audio amplifier. And on transmit, you're switching a power amplifier. Actually, someone can build this, right? VFO can be just 1 transistor. BFO can be 1 transistor. Audio amp can probably be 2 transistors. Mic is another 1 transistor. So in 5 transistors, you should actually be able to get a radio going. So why don't we just build a radio like that? So I have actually developed a web version of a utility which comes with Experimental Methods in RF Design, the book. It's called Cascade, and I'll extensively use that now to plan a new radio. So here it goes. So these stages, I'm going to populate them into this calculator, which is available on my website called Cascade, in which, if you see the top line, what I'm going to do is I'm just going to write down the name of each of the blocks, like these blocks: bandpass filter, mixer, SSB filter, etc. So that's written up here, and the gain or the loss in each one of them, and the noise figure of each of these, and the IMD figures for all of these. So here, I'll just explain this a little bit, how it works, and it works fabulously well after that. The gain for passive blocks like filter is negative. So for example, if there's a double tuned circuit, you might lose 3 dB there. Diode mixers, you lose 7 dB. Crystal filter, probably another 3 dB. The second mixer, you lose another 7 dB. Then you will have an audio amplifier where all your gain is, which is about 80 decibels of gain here. Accordingly, I've filled up the noise figure. The noise figure for lossy components like RF filters and mixers is the same as their loss. So 3 dB, 7 dB, 3 dB, 7 dB. And for the audio amplifier, I've put it as 6 dB, which is a nominal gain for a noise figure for a transistor like a BC547 or a 2N2222 or a 2N3904. And in the bottom here, I have put up the guesstimated OIP3, which is their intercept figures. And for the RF filter, it's about 50 or more, because RF filters hardly distort. The mixers we know, like AD1 or our own diode mixers, which we homebrew with 1N4148s, their input intercept is 7 dB, and then you lose another 7 dB in gain, so it's about 8 to 7 dB. Crystal filter another 50. Then after the crystal filter, you don't bother with OIP3 because the distorting signals have been filtered out, and only the signal that you are interested in is going through. So I've just put the rest of the stages as 200, 200, 200. And at a bandwidth of 2500 hertz, you press the evaluate button. Now, the noise figure here is 26 dB, which is pretty high. On the other hand, the IIP3 is also very good, which is 17 dB. And we have a dynamic range of 87 decibels. So in one way, this is a fairly good radio because it's got almost 19 dB dynamic range. The problem with this is that the noise figure is pretty high, which is 26 dB, which comes to about, probably 0.5 microvolts as the minimum discernible signal. It can still be a good radio for 80 meters and 40 meters, but not beyond that, certainly not for VHF. So if you see here, what's happening is that until we get to the audio amplifier, there's a lot of losses happening here. And in order to make up for these losses, what we are going to do is we are going to add some amplification before the mixer, because the mixer is the first really lossy stage. So let's imagine that we have added a mixer here, a post-mixer amplifier with 16 dB gain, 6 dB noise figure, and an OIP of, let's say, 50 dB to begin with. And we evaluate this, and now we will see that the two-tone dynamic range can increase to 92 dB, right? Now, but the noise figure is still about 18 dB of noise figure here, right? So the noise figure is still looking pretty high. And what we have to do that is probably add a little more gain. Let's see what happens if we add a little more gain. So here what we have done is I've put the post mixer to a more reasonable value of 20 dB OIP3, and I've increased the gain of the post mix amplifier to 40 dB. Now you see here, the noise figure still stays at 16 dB. So increasing gain does not always translate to increase in sensitivity. You can actually play around with this on my website and see how this works. The noise figure is still about 16 dB, which is about 0.15 microvolt sensitivity. We have to do a little better. The dynamic range has gone down to 76 dB because of this high gain. So I'll decrease this gain back, but in order to increase the noise figure, we'll realize that between the RF filter and mixer, you've already lost 10 dB. So, and the next stage, the post mixer has its own noise figure of 16. So just here itself, that is 3 plus 7 plus 6, we already have 16 dB of noise figure. So what can we do? What we'll have to do is we'll have to add an amplifier before the mixer. So let's do that. So now we have added another RF amplifier between the mixer and the RF filter, which is still having a -3 dB loss. And the noise figure of this RF amplifier, which is a low noise amplifier, is 3 dB. And now if we calculate this, we see that the noise figure has come down to 8 dB. Still not good enough for VHF work. And the MDS is now improved. It's -132 dBm. The dynamic range has fallen to 81. But on VHF, there are hardly any kilowatt contesters who are pointing the Yagis towards you, so it's perfectly fine. There are other baddies around, like possibly the FM broadcast, but we'll come to that in a little bit, how of what we can do to mitigate that challenge. But you see here that the RF filter itself has a -3 gain, loss, a loss of 3 dB. So you're starting with a noise figure of 3 because of this itself, and the noise figure of the RF amplifier following that will add up to it. So it will not really dip much below uh, the figure of 6 dB here. So what can we do? We can add some amplification before this RF filter. Okay, and we need this much of RF filtering because if you do not have extensive RF filtering on VHF, everything from cellular, QRM to FM broadcast, etc., can get through it. At least in my location, there are a lot of FM transmitters within 7-8 kilometers, each transmitting 25 kilowatts. So, and it's all direct line of sight. So in the next one, when we plan this out, there is a pre-selector, which is just a single LC circuit, followed by the low noise amplifier, followed by a triple tuned circuit where I can take an even more loss of 4 dB, then an RF amplifier, mixer, post mixer amplifier, SSB filter, etc. So here, if you see, now I am able to take the noise figure down to 3.3 or 3.5 dB, certainly below 5 dB. So this is the lineup that we can go for. And it still has a good dynamic range of 70 dB, not too great, but if you want sensitivity, then the dynamic range is going to go down. So this is the lineup that we are going to do. But the other very interesting thing is if you just keep adding up all these gains, there are 3 amplifiers of 16, 16, 16, that is 48 dB of positive gain before the SSB filters hit. And you have 3 and 7, 10, 14, about 14.5 dB of loss. So all in all, we have a positive gain of about almost 20 decibels going into the or rather coming out of the IF amplifier, out into the IF stage. As a result, after the SSB filter, you do not require an IF amplifier because there is just enough gain here that we can directly go to the second mixer, which is actually a detector in case of a receiver and a modulator in case of a transmitter, followed by an audio amplifier with 6 dB gain. So it's unusual that there is no IF amplifier required after SSB filter because we needed all this gain in the front end itself in order to make it low noise. I should tell you that my primary aim with this radio is to work the satellites. As a result, I needed it to have fairly low noise figure. For others, it might be different, but that was my personal target. So this is what we are going to build, right? And here, now if you see from here, the LNA was 16 dB, RF amplifier was 16 dB, and post amplifier was 16 dB. I can reduce the gain a little, nudge it around, and still maintain a noise figure of less than 5 dB. So here I have actually tweaked this, and here you can see that the low noise amplifier has got 10 dB gain, RF amplifier after the filters got 16 dB, post mixer amplifier is 10 dB, and even now the noise figure is held down to 4 dB. So this we can tweak our lineup to have minimum gain required to hit the noise figure while maintaining a good OIP3, and now the two-tone dynamic range is above 80 dB. So we need to build amplifiers, if you see here, with 20 dBm OIP3, which is pretty easy to do. And each time we control the gain using feedback to either 10 dB or 16 dB, etc. So with this, we are done with this. And this is what Wes says, at all times, that simulation is the greater experiment. Okay, so that's the amazing part, that this itself is an experiment, and by simulating it, you can know what individual blocks are contributing to in our final radio. So very good. Now that we have fixed this, there is one problem that I would like to start, which is the FM broadcasts on VHF. And in any case, On the converse side, while transmitting, it's also important to hold your spurious emissions down, because on VHF, they are far more stringent, especially in Great Britain and in Europe, where they require the spurious signals to be down by 60 dB. So when you're transmitting out, the image of your IF should not be more than 60 dB, which essentially means that the band pass filter which you're going to use in between the stages should be sharp enough to cut out the image frequency. Okay, so with that, let's launch ourselves into doing that. So okay, so sorry, yeah. So this is the just forget about what's on the left, but if you look at what's on the right, you see a sharp peak here, and the center of the peak is about 146 dB. And I have put this marker here at 123 dB, at 123 megahertz, and you can see that that is down by 63 dB. So at 120, and that's, you know, if you're using, let's say, about 11 megahertz of IF, the image would be falling here, because the oscillator would be 11 megahertz away from 146, which would be at 135, and the IF would be another 11 megahertz down. It would, you know, come to about 124 or so. So this is a triple tuned circuit. The circuit is on the left, but let's not bother with it right away. I'll just come back to it in a slide or two. So this is how a filter really looks. We basically have a series of resonators, which is an inductor and capacitor, and we couple them together so that the energy from one couples to the second, and from the second to the third, and then gets out the other way, each time filtering it more and more. And I have put these stars here because these are the coupling capacitors, and depending on the choice of these capacitors, you will have different shapes of these filters, whether it's, you know, Butterworth or Chebyshev, etc. These are mathematically chosen, and the maths is pretty easy. But, you know, if you don't like the maths, you can use some of the filter calculation programs where you just plug in the values, say how much bandwidth you want, what kind of a shape you want. The two filters that we often use to build our RF filters are either Chebyshev or Butterworth. The Butterworth filter has gentle slopes, which means the skirt is not sharp, but within the pass band, it's very smooth. Whereas for the Chebyshev, the skirt is steep, but within the pass band, there are ripples. So you basically trade one for the other. Ripple inside the pass band is traded for the steepness of the skirt. So the choice of these capacitors will determine that. Now, these capacitors become very, very small when you come into VHF. For example, on 14 megahertz, you might use 2.2 PF capacitors to couple between these inductors. Now, if you just scale that up to 144 and, you know, divide everything by 10, you're looking at 0.22 PF capacitor, and that's not possible to get. So what you do is what's here in the third line, which is tab down on the capacitor. Tab down the capacitor in whatever ratio you want it to be tabbed down, and then couple that together. So the third line here shows you coupling, where you can use higher value capacitors, but use capacitors like a tab down, like you would, you know, tab down on an inductor. You can tab down on the capacitor. Much more definitive way of doing it. And then in the fourth line, you will see that that's how you can also couple them to the endpoints of the source and the RF out, right? So using this, the filter that we have now built is this. What you see here is that I do not have access to trimmers here, and what I have done is I've used only those parts which are available of Mouser, because Mouser delivers parts now to every part of the world. So I've just used 10 and 2.2 PF capacitors everywhere. The 4.7 PF capacitor can also be made by paralleling up to of 2.2 PF capacitors. So if you just have these two capacitors, you can do that. The coils needed to be 75 nanohenry and 88 nanohenry and 75 nanohenries. what you do is you just wind 4 turns on a quarter 20 bolt, and then using a toothpick, you can pull the turns apart for the central coil and push them closer to each other for the 75 nanohenry thing to get it on the frequency. So now with that in place, you can simulate this either on LT Spice or on the LAD build and GPLA. That's what I have done in my case using the EMRFD tools. And this is finally what it looks like. The one you see on the left is basically the same filter. So you design this filter, save it, and then you run it through the GPLA program, and the GPLA program gives you this particular shape. So that is the filter shape. Now here, the more you move away in your IF, the better is the suppression of the image, until you get, for example, inside the FM broadcast passband. For instance, if I had taken 20 megahertz as the IF, the image would have been 20 and 20 away, which is 40 megahertz away at 104 megahertz, which is spot on FM broadcast station of Hyderabad, which plays rock music all the time, which I like, but not when I'm operating. So instead of that, we choose something which is closer to 11 or 12 megahertz. And here, this one thing which I learned is never to use an IF frequency which is an even number like 12 megahertz or 10 megahertz or 5 megahertz, because all these Arduinos and Raspberry Pis have clocks in them which work at 8 and 16 and 10 megahertz, and they generate all these spurious markers which are at 1 megahertz and 500 kilohertz and 250 kilohertz, etc. So there's always a possibility that you land up with something inside your IF passband, which is why it's a good idea to pick up an IF frequency like 11.059 megahertz where crystals are available. In my case, I wanted to move away, so I took 14.318 megahertz. So that's the choice that we made, which is 14.318 megahertz crystals. They are available. I had never made a filter with those frequencies, so I wanted to see how that works. So the next thing is that now I would like to, before anything else, make a sort of a digression here to how to test these RF circuits. So basically, to test one module at a time, it's pretty simple that you have something which generates signal or signals. If you'd like to see how two signals make it through together through a particular circuit, and then you detect these signals here. And the important thing is that the detector at this end needs to be tunable. And this was a problem with Sweeper Reno. If you were listening to Tony Fishpool's presentation, and there you saw that in the skirt of the filter there were these small peaks on sides which were actually the harmonics of the signals which were making through the detector. What I mean is this. Now, for instance, imagine that this was a filter and you were trying to sweep a 10 megahertz filter. So when the signal came to 3.333 megahertz, its third harmonic would be still 10, and it would go through this filter and the detector would detect it, because the detector does not differentiate between 3.3 and 10. So which is why it's important that the detector also moves along with the signal source. And this is simply how you do this. And there are various ways to go about doing this. I mean, we need to measure things like, does a filter work? What's the gain of an amplifier? Are the ends matched well at 50 ohms? That's SWR. What's the SWR of these circuits? Does the circuit overload easily, etc.? Now, you could use a good old signal generator and your RF, detector, which is a radio, a general purpose radio. But the challenge is that the signal generators have to be fairly wide range. For VHF work, it should at least go to 250 megahertz, and it should be able to step within, in steps of 10 hertz or 100 hertz minimum. And the detector should have at least 80 decibels of dynamic range for you to be able to measure the filters properly. Now, an easy option here is to just use an Arduino to control an SI5351 for these signal generators. And you could use one of the AD8307s to easily measure 90 dB of range at the IF of the receiver. So I put this thing together after Sweeperino. The second evolution of this was a thing called Antuino, and I hope to be able to show you this. So the Antuino is a very simple, very useful thing. It's an SWR meter. It's a spectrum analyzer. It's a signal generator. It's a power meter. It's even a voltmeter combined into a small, well-shielded box with its own built-in battery. You can build this easily in an evening or two. As you can see, it's a fairly simple circuit diagram. And the key thing here being the SI5351 and the AD8307. The SI5351 kit is sold with this thing soldered. It's very difficult to solder by hand. Hans sells it from QRP Labs for about $7. The Arduino Nano hardly costs about $2. Then you have the AD8307, and as Tony was saying, the SMD mounted PCBs are available for a couple of dollars. So all in all, for about $20, you can put this thing together. If it's too much of effort, you can spend far much more money and buy it from HF Signals. But there is import duty, and it's certainly not worth spending so much money if in 2 evenings you can finish it off. Now, I'll just explain the circuit. It's pretty simple. The signal comes in here, and there is an AD1 mixer which mixes the signal and produces it into an IF of 25 megahertz. It is a 25 megahertz IF radio with 2 crystal filters cascaded so that the skirt is very sharp. And in place of the BFO, we have an AD8307, which is measuring the signal in dB range. Now the Arduino is programmed to sweep through frequencies and plot them on the display, which is a 28 by 64 display here. I used a monochrome display. It doesn't look too sexy, but it works in the sunlight. It's not very noisy. And the output, the signal output is basically clock 0 through an attenuator pad. And the interesting thing here, if you see, is in the input, we have an SWR bridge, which measures the SWR if the clock 1 is actually driven by one of the outputs of SI5351, and that's how you can also measure the SWR for it. So that's what I use. You can use something else as well, but for example, Nano VNA can do this job just as well, except that it will not be able to measure the distortion products, as it does not have a good filtering system in the front end. So with that, this is the filter that we built. And as you can see that I have used a silver wire right now. I started using silver wire, but it actually didn't work because when I was compressing these turns together, it started shorting. So it's built on a copper clad board, and here I've cut these squares on one side of the board and soldered all these capacitors together. And over this, I soldered the BNC connectors directly onto these pads themselves. There are no trimmers because Mouser doesn't sell any. These are all air core, and the central inductor has to have more inductance, so I've pressed this a little more. I built this, and then I measured this. There is a glitch here in the software, but as you can see that the thing was pretty smooth. The leftmost part is about 144 megahertz, and I just got 4 dB of loss, which is pretty good, And with this, the RF amplifier was done, and we had to now move on to the the VHF filter has been done, and we'll now move on to making the RF amplifiers for VHF. So this is another picture of the same VHF filter, and now I had to insert these shields in between so that the skirts were sharper. Otherwise, the signal was getting, was jumping from one inductor to another through mutual inductance. So with this, we'll now come to the RF amplifier. So I just use one kind of RF amplifier all the time, which is an RF amplifier with feedback. Now this amplifier is pretty simple and straightforward. What you do here is that there is a load resistor and an RE, and the ratio between these two determines the voltage gain. So if this is, let's say, 1000 RL and RE is 10, then you have a voltage gain of 100. And the only simple trick is that the ratio of RL to RE should be the same as the ratio of RF to the Rn, or whatever your Zn is. As long as you do that, the amplifier behaves beautifully well. The problem with having a resistor in the collector load is that there is a voltage drop across the resistor all the time. As a result, the voltages cannot swing much. So what you can do is what I have here on the right hand side, which is replace the resistor with an inductor. And in this case, we basically couple this to an external load, and that load actually determines what the RL is going to be. And at times you want the RL to RE ratio to be high, but you want it to match to 50 ohms on the other side. So in which case you tap down this inductor, and you use a balloon of sorts where there are two parallel windings, and this is an equivalent of that. The other way of bringing the output impedance down is by using an emitter follower, where the output of this emitter will essentially feed any impedance, because it's a fairly low impedance output here, and you just put a series resistor for whatever output impedance we want. It's usually 50 ohms here, so this will be followed by 50 ohms resistance. So using this, with the filter done, now we will, as you saw in our block diagram, that there are 6 stages of RF amplifiers which have to be built: post mixer, RF amplifier, and all right. Can you guys see the desktop again?
Yes, we can.
All right. My apologies. So now, one problem of making feedback amplifiers or any amplifier on VHF is that we do not know what kind of toroids will work. The FT3743 is the standard for our regular work for HF. So would this actually work for VHF? One doesn't know. So what I did is I actually wired up a VHF simple jig where I could see, there it is, oops, there. So I just wired up a small transformer, FT3743, and found out whether this works at 145 megahertz. Now, if you see here, it's actually going through an attenuator. The loss was less than 1 dB. Okay, so this was a big revelation to me, that the FT3743 can work as a broadband transformer on 2 meters. And that really made me extremely comfortable with the next thing, which is that I made a feedback amplifier with the FT3743, and I used BFR106. Now, these are the transistors that I use all the time. They're very cheap, about 15 cents in bulk, available on Mouser. The only unfortunate downside to it is that they are surface mounted devices. So it's unless you're putting it onto this checkerboard kind of a thing, or you have some other jig to solder them on, they are a little difficult to do. But here it comes. You can cue in the claps and the boos, but I will show you that I managed to make it ugly with an SMD transistor here. So this is my brag shot. So what I did was, actually I first soldered the base onto the bias resistor, which is 470 ohms. And with this, it's a simple feedback amplifier, and I'll give you the circuit in a second. And this actually worked pretty well. It's built the ugly way, just like we build HF. And what I realized is there's nothing to be frightened of for the VHF work either. So, and here is what it looks like. So this was, done on 21st August, which is, we built this amplifier and it works fairly well. It had 18 dB of gain on 2 meters. And even when I dropped this voltage to 6 volts, it still was giving 17 dB. But the problem was that you see on the right, when we connect them back to back, the gain was less than 5 decibels. And this, I'm guessing, is because of the feedback which happens from the transistor which is switched off. So that's what was causing this entire problem with the with putting two of them back to back like you do for bidirectional transceivers. So I was back to the drawing board, and then I switched back to the termination insensitive amplifiers, which is coming up here, this one. Now, instead of using 3 transistors, I just used 2 because with the Darlington pair, the gain was going down. So this is the simple transistor block, amplifier block that we will use throughout everywhere. And this was done on the 29th. It gives 13 dB gain at 12 volts, 11 dB gain at 6 volts. And even when you put them back to back at 6 volts, it was still giving 11 dB gain. The preselector loss that's showing as 2 dB here was actually because I had not tuned this. So this preselector just has a coil and a capacitor here. So with this, we had sorted out our entire business of RF amplifiers, and the RF amplifiers could now be built, right? The next thing that I had to build was the VHF mixer. And for the VHF mixer, what I did was again build it as a prototype. You'll see here shortly. Okay. So this was, it again used 2 FT 3743 toroids with 4 turns each. And I used a 2-tone generator. It's a very simple circuit of 2 crystal oscillators with 2 buffer amplifiers each. They are mixed here in a hybrid coupler, and through a low pass filter, they are fed to this diode mixer. Both these crystals are off from each other at about 10 megahertz, 10 kilohertz. You can see that this inductor here pulls one crystal down. And the local oscillator was this Radiono, which is essentially an Arduino with an SI53 mounted on this 5351 mounted on this board, which feeds in as a local oscillator at about 130 megahertz. So the output of this was then measured to see how well this works. And here you can see that the input from here, from the 2-tone generator at 14 megahertz was minus 10 dB. And this output here is at 144.319. It's exactly minus 17 dBm. So the loss from minus 10 to minus 17 is just 7 dB. It's exactly what a regular diode mixer does. I tried with first 1N5711, which is Schottky diodes. And then later, you can see down here, I made a bridge with 1N4148, and it gave us a horribly bad loss of minus 20 dB. Let me show you that. Oh, I have not included that here, but I was really surprised until I found out that the 1N4148s here were actually Zener diodes, and I had packed them in the wrong bag. So after that, I put them back, and even the 1N4148 worked at VHF. So that is actually the big learning here, that FT3743 works. So do the 1N4148 diodes. So with this, now I got to start making the front end, which is from preselector to the IF output. And I basically use a copper clad board, and I score this with this acrylic cutter. Each of these squares is about 5 mm to a side. And I built the front lineup. So this is the preselector, this is the low noise amplifier, followed by the triple tuned circuit, and then the RF amplifier. First, we check this RF amplifier. in one direction, then the other direction. Then we move on to include the triple tuned circuit, tune this up for a maximum peak, both directions, and then move this thing further down so that you have the entire front end now completely working in both directions. Most of the time, the trouble I had was that I had not soldered the other side of the SMD properly. These SMDs are all 1206 size. They're about the size of a quarter watt resistor, actually. They're not difficult to solder at all. In fact, they're easier to solder because you don't have to keep going back and forth between top and bottom layers of the board. Wherever I wanted a ground, I basically drilled a hole and put a small pigtail through it and soldered it to the ground onto the other side. It works pretty well for VHF work. So what you see here now is a completed board, the board towards the top, along with the mixer and the post-IF mixed amplifier. So 144 to 146 gets in on the right-hand side, and 14 comes out here, or 14 comes in here, and 144 gets out there. In the future, I want to be able to add a parallel module of not SSB, but instead of SSB, CW or FM here, and make it into a multi-mode rig. About the second board, we will come to it now. So until now, if you see that we finished pre-selector, low noise amplifier, triple tuned circuit, followed by the RF amplifier, radio no, post-mix amplifier has been done. Now we have to do the SSB filter, followed by an attenuator pad to terminate it properly. Then the product detector / modulator, a BFO, mic amplifier, LM386, and a new type of an audio preamplifier, which Wes has just recently released. It's a termination insensitive amplifier for audio frequencies. So this has been incorporated here as well. This capacitor and resistor, this is a 50 ohms resistor, and this capacitor essentially grounds all the non-audio frequencies coming at the IF port into a 50 ohm resistor and terminates them properly. And the audio is allowed to escape both ways. Actually, I've drawn this in the wrong way. Even the mic has to be connected onto this other side of the inductor. So now the crystal filter which we had to design can be understood as this. Start with a low pass filter. Okay, we all understand low pass filters fairly well. Now replace the inductor with an inductor and capacitor. So you now make this into a band pass filter. And the band pass filter, a crystal can actually be considered as a coil and a capacitor in series. So you can replace the inductor capacitors with these crystals. Now, in order to design this filter, you need to know what this capacitance is, the internal capacitance of the crystal is, and the internal inductance of this is. And that can be measured by actually plugging this crystal filter into an oscillator. So you know what the value of the frequency of the crystal is determined by the product of, or the multiplication of this inductor value into the capacitor value. Now onto this capacitor, if you add another capacitor in series, the value is going to shift a little, and that shift will tell you how much of this is the inductor and how much of it is the capacitor. And to do that, there's a very simple circuit. And this is a circuit given by G3UUR. Let me see if I've included that anywhere here. No, I have not included that, but you can look it up. So with this, I measured the inductor and capacitance, the internal inductance capacitance, and designed this. There are various programs available to design this. So I use the one which comes with EMRFD. Initially, I used 100 PFs for all these coupling capacitors and 100 ohms as termination. And this turned out to be a little wider than I would have liked, So I did a next iteration of this with 68 PF, but with 50 ohms termination, and that worked pretty well. So let me just see where that is. I should have the inductance. Okay, anyway, I don't think that I've included that here. So this now is the crystal filter followed by the product detector and the beat frequency oscillator. These are standard circuits, and I will come to that, the actual circuit itself, in a little while. The next thing which I had to design was on the transmitting side. And for the transmitting side, it was important to design the VHF low pass filter. So this is the VHF low pass filter designed and then again simulated here. And once this was done, I fabricated it using 3 turns on this quarter 20 bolt. This bolt actually is pretty useful because it gives very accurate windings, and then you can actually keep the winding on the bolt when you solder this in and then gently take it out by unscrewing the bolt away. So this here, instead of, if you see this here, 25 and 50. So in place of the 50, I've used doubled up 22 PF, and in place of 25, I've used 22 because the capacitance of the pad itself adds to it. So just using one capacitor value, I managed to get the triple tuned circuit going. And this was the VHF LPF. And the measurement was that at the second harmonic of 145, which is 290, the loss was minus 39 dBm, and at 435 megahertz, it was 40 dBm. So with this, we had the low pass filter going. And here, as you can see, is the first feedback amplifier which I had made, just increased for far more standing current of about 40 milliamperes. And there are 2 relays which switch this in and out of the signal path. So on receive, this coax carries the RX signal directly from here and into the rest of the exciter. But on transmit, this amplifier is switched in. And the exciter gives about 5 milliwatts of output, and this boosts this to about 100 milliwatts of output. So I had to make a chassis for this, and I basically built one out of scrap circuit boards. There are 3 front-end audio connectors for mic, speaker, and key. There is something for the volume control and a front BNC connector and the encoder and the radio no, which I had explained is just Arduino plus the SI5351. So this is the complete transceiver, fully assembled and working now. It has a couple of glitches. The software is not complete yet. I have not yet implemented receiver incremental tuning, etc. I'd like to add a module which takes this power to about 5 to 10 watts to make it, directly work with the satellites. But otherwise, this is complete. And here is a complete circuit diagram of this radio. This is available in the link that I have shared and which I'll share again with you, in the next slide. But it's a fairly simple circuit diagram, as you can see. The same amplifier block which you see here and here and here and here as it's used, and slightly modified version of this with Darlington pairs is used for HF. So it's exactly the same circuit diagram. It's actually not very different from the circuit diagram of the original BITX, except that that you have got VHF running through this. The beat frequency oscillator here is a little different. This is, this gives far cleaner output than the BFO, outputs which we've been using earlier. I've used BC 857s here, which are SMD versions of BC 147. Very good transistors and, very British. I've seen a lot of RSGB books use them. The other important thing is that the mic amplifier has an emitter follower after the mic amplifier. This is because the modulator expects a driving impedance of 51 ohms, and usually we drive it from the collector of the mic amplifier, which is not at 51 ohms. So with this, I had to actually reduce the gain of the of the mic amplifier, because the microphone itself provides you about 50 millivolts of signal, and the detector requires about probably 100 millivolts or 200 millivolts of audio. As a result, not too much gain is required. As a result, this has just 1:4 gain ratio. This is 1K and this is 220 unbypassed. And here is the other beauty. This amplifier is a feedback amplifier. As you can see, there is a 2.2K resistor here. This is a feedback resistor. And again, if you see this ratio of 1K to 22 ohms. This is giving a gain of 50. And the same ratio will apply here as well, which is 2.2K versus 50 ohms. So this is a balanced feedback amplifier. The output is taken through an emitter follower, and the emitter follower again has another additional 470 by 47, another gain of 10, which allows us to use an LM386 without that pesky feedback resistor, which we have to add between pins 1 and 8 to increase the gain. Instead of that, we actually have a negative gain added to this amplifier to make it, work really well. So with this, we complete this description. Thanks first to Steve, Nick, Anthony, all you guys for this dream spot for me to come and speak here. Thanks to Wes, W7ZOI, for the book he wrote, along with Rick and Bob, and more particularly for the amps that were used in this particular radio. Now, the main inspiration of this kind of radio actually came from Bob, W7PUA, for his DSP-10, although this is an analog rig, but the architecture remains the same. My friends and partners in crime, Sasi VU2XZ, Anil VU3DXA, and Venu VU3BVA helped me, every way from testing to giving ideas and, waking up at odd hours. All the details are available on my GitHub. And for any further discussions for the 2-meter rig, the BitX20 will be open to do that. So that actually brings me to the end of this. And I would like to come back to, I don't know whether you guys can see me.
Yes, we can.
Oh,
yes, we can. Sorry about that. And there's a good reason you forgot to plug that laptop in. I understand you've been busy working on this on these slides in this project for the last 24 hours straight. So,
oh yeah,
we've all done that before. Ran out of power in the middle of something. So we understand that. And great presentation. We have a couple questions. The first question was, what do you use for your schematics, such as the one you did with the Arduino example?
well, I use an open source software called KiCad. And that's a software that I've been using for a long time now.
Okay, very good. And the second question is, aren't there any problems with stray capacitance between the squares on your PCB at VHF, and how do you solve these problems?
Yeah, so these problems would arise mostly in the bandpass. And if you see that I've used these air core coils where you can, tweak them a little. So I do that. One second thing is I keep the capacitances that I actually use to be about a PF less than what actually needs to go in there. So that's actually how I manage to, keep these capacitances by essentially making the filter tunable so that those small differences can be overtaken.
So you're using the known capacitance of the board in your calculations for your needed.
Of sorts. I mean, the capacitance would hardly be about half a PF for a 5 mm by 5 mm FR4 board.
I've just posted the link for your IO group, and there was a question about some of the information on the GitHub. They said they couldn't find anything other than the README and the license right now, but
yeah, I'm just uploading everything right away.
See, he's been working on it. He's still working on it right now during the presentation. I'm sure there's a third hand over there still soldering too, isn't there?
Well, almost. No, actually, I can show you that it's all complete. But I've just added this. I actually forgot to commit it, which is why it did not come through. But in a couple of minutes, you will have everything there. Okay, it's already there now, so you can actually download everything. I've also included the design files to in addition to the PDFs and the schematics.
I also posted in the chat the link to the Cascade calculator. I'll repost that again also.
Yeah. There's also a feedback amplifier on the website. So if you just go to vu2ese.com, you can see a feedback amplifier calculator, which is similar to that.
Very good. If we have any other questions, please remember to put your your questions in the Q&A so that I can see them. Next question: Have you an idea of the approximate receiver sensitivity from the prototype?
Oh yes. So First I calculated it to be less than 5 dB. Okay. The second thing is that when I plug in the antenna, even a small whip, I can hear the noise go up. Now, in fact, this is very interesting because when I was plugging in the whip antenna, the noise was not going up to begin with. And that's when I realized that the audio gain was low. So I had to up the audio gain. And if you look very closely at some of the photographs, you will see that I had to actually solder some additional resistors to bring the audio gain up for the new termination insensitive audio frequency amplifier, and that actually brought it up. So it's actually probably south of 5 dB. So that's probably where the noise figure is at. I do not have a calibrated noise source, so I really can't say, but that's my guesstimate.
Very good. A number of comments on from very pleased UBIT users out there, and a number of people that are very intrigued with the project and ready to start building their own. There is a question in the chat. Again, remember to put your questions in the Q&A, but I'll take care of this one. How did you stop the intermod within various parts interacting with each other? And was there an easy fix to this?
All right. So I guess what you mean is that signals being picked up from one place to another. So if you saw the the second last picture, which was of the entire rig itself, there are very few coils, which usually are the ones which cause this. But I did put a shield around the triple tuned circuit, right? There is a shield I made with very thin copper sheets, which are available in the market. I think they're used in transformer shielding. So I use that, number one. Number two is I've used a fairly open layout. I mean, this thing is about 8 inches by 6 inches. So it's a fairly large radio. Instead of making it small, I tend to make them a little larger than needed so that I can space these things out. The final thing here is this. Everything works at 50 ohms. Everything is well matched, so there are no reflections happening. And 50 ohms is low impedance, and because of low impedance, it's very easy to keep the interactions down. For example, with valve amplifiers, or for example, if I had used dual gate MOSFETs, they are all high impedance devices, and there's a great chance that they will interact with each other and go into self oscillations. But if you're using feedback amplification and you're keeping the gain down to what's absolutely required, and everything is tuned or tweaked to work with 50 ohms, then you won't have the problem of the stray couplings.
Well, very good. On your mock-ups, how did you ground the BNC connectors? It looks like they're floating.
Yeah, I mean, I actually have not checked the circuit diagram entirely, but it needs to be fixed, and I'll in the couple of days, once I wake up from this, I'll get to fixing it. I actually, last night I did this at about 3 a.m. Then I was up again today at 7 a.m., just to get the slides in. As I said that, most of this work was done in the last 1 week because that's when I got freed from other work. So I'm sorry if the documentation is poor quality, but I'll certainly, fix it very soon. I'll have people looking over it. And in case any of you find any problems with it, just email me or, catch me on the group and let me know.
And of course, the question you're definitely expecting is, when will the kit be available that they can buy?
Okay, the kit will not be available, all right? The reason is this, that this one requires you to tune up the filters yourself. And that actually is something that can't be done on a mass scale. So this is more like gourmet cooking, right? I mean, this is, whoever it is, the master chef kind of a thing. This is more like your own craftsmanship. So take your time, build it one circuit at a time. What we have instead of this, for example, what HF Signal sells is the Antuino or the Nano VNA. Instead of a kit, I would really urge you to invest in one of these measuring instruments and use that to build your own knowledge base and experience base, and start building small circuits and start knitting them together.
Very good. Again, some more thank yous on the excellent presentation. Very impressed. And again, if you have any Q&A, please put questions in the Q&A, and I'll be happy to forward those on. Well, thank you everyone for attending this very good session today. And please follow up with the information that Farhan has provided on his GitHub site. And again, I will post that one more time here in the chat. Make sure you copy it down so you have this. And also consider joining the Groups IO, which I'll also post there for further discussion, so you can continue the discussion online later on. So both of those links are now in the chat. We got a couple final questions here that just came up off the bottom of my screen. As an old-time HBer, most of the projects now have Arduino or Raspberry Pi. I have no experience with either of these. Any advice?
Well, my advice would be this. I ran out of time. I was not planning this to be an Arduino or an SI5351 based radio. And I'm going to work on making this a VFO based radio. And the reason for that is pretty simple. On satellites, the Doppler is already shifting the frequency. So you don't have to be really accurate on the frequency. Some of the programs require, can automatically adjust the frequency, but actually even on FM, the signal itself is about 15 kilohertz wide. So what's the point in having 100 hertz stability requirement? So unless you are running, some digital modes like the, FT8 or one of those modes, a VFO should be able to do it. So a premix VFO, for example, 11 megahertz VFO or 12 megahertz VFO mixed with 125 megahertz should get you up to the local oscillator which is required, which is around 130 megahertz. Not too difficult at all. Exactly the same thing. Make a triple tuned circuit, make a diode mixer, mix a crystal oscillator with the VFO, and you're done. So that should be pretty easy to do. And I plan to do this in the following days and make this into an all analog radio. One reason for that also is this. One of the reasons why I've built this radio is to take it along with my cycle rides. Me and my XYL, View2 TUV, Humera, we actually go on cycle rides about 50-60 kilometers. And I always wanted to carry a small radio with me, not HF, which is why I've built this. And it needs to have very low battery consumption. So, not 150 milliamps, but, probably something in the order of 70 to 80 milliamps, or probably even 50 milliamps. So the idea is to make this VFO based and an all analog radio. And frankly speaking, the reason why I'm doing that is I'm completely tired of this SDR, which I just completed, the SBTX, but I'll keep that for another time. There's too much to explain.
Tony, I could also throw one little quick thing in that if you're worried about playing around with Arduinos and Raspberry Pis, just jump in. There's a lot of good resources out there, and they're really not that hard. I was able to figure my way through them, so I think that it's a good learning experience, and it's not that difficult. And the libraries are very supportive for various projects. The next question is, again, could you give us the name of the schematic drawing program you used?
It's called KiCad.
KiCad.
Yeah.
Very good.
Or KiCad. I don't
KiCad.
know. Yeah. It's an open source software.
Yep. Someone put.
Yeah. And it's been actually, developed by some of the,
the next question is, interesting that you didn't consider a VHF converter in front of the BitX, i.e. a double conversion architecture.
Well, yes, but there was no need to do that. There would have been just too much gain. And it's pretty simple to do a single conversion superhit itself, because once you have something converting down to, actually, if you see that this system converts to 14 megahertz, the IFS 14 megahertz. So you could just use the first part of it and use it with the BitX backend. But there is very little to, left to the BitX backend at all. All you need is an SSB filter and a diode mixer. So that's actually the interesting part, that it would be an overkill to do that, because the hard lifting is already done of converting VHF to HF. All you need to do is convert the HF to audio and you're done.
Last question. Any news on your SBTX?
Well, SBTX is here.
There it is.
So I'm actually assembling the first of the things, but there's been oops. The this was supposed to go in this way. It's actually going in the other way around. So I have to actually redo the circuit board layout. But it's on the way.
Those connectors are always the hardest part. That's the part that
I
always
just
bites me
forgot.
too. Well, thank you very much for your presentation. We want to keep this on time, or Nick will dock all my pay for this, and you'll get no pay either. So thank you very much. We really appreciate it. And again, you might be visiting the chat rooms a little bit later, the coffee room. So look out for
I'm
Farhan,
around.
and you can
I'm going to be around, for
interrogate him in more detail on. So thank you very much. And with that, we'll go ahead and we'll close the webinar, and I'll stop the recording.